Well, thank you all for coming to hear about the James Webb Space Telescope. I hope you can hear me. I'll speak loudly. Space telescopes are our most powerful tools for looking back in time. Traveling back in time is the stuff of science fiction, but looking back in time is science fact. And it results from the finite speed of light. Because light travels at a finite speed, there is a transmission delay. So if you look at the person seated next to you right now, you're not seeing them as they really are. You're seeing them as they were a few nanoseconds ago. Nanoseconds are, imperceptible, so you don't notice that delay. But when we look at objects farther and farther away, the delay becomes more pronounced. For example, if we had a magic switch that would turn off the sun, we wouldn't know anything happened for 500 seconds because that's how long it takes for the light to travel from the sun to the earth. And if we look at the closest star, we see that star as it was 4 years ago. And as we look at more and more distant objects with telescopes, we look farther back in the past. And looking back in time with telescopes is much of what modern astronomers do. Now, the James Webb Space Telescope was conceived in the late 1990s as a mission to connect the dots, if you will, between this famous image and this famous image in context of this cartoon of the history of the universe. This is a picture of the oldest light that was recorded by NASA's COBE satellite. A Nobel Prize was awarded for that. And this is what the universe actually looked like moments after it became transparent. About 3 minutes into its life, it became transparent, and this is what the light looked like when it escaped. This image is, back in the 1990s, was the deepest image that the Hubble Space Telescope had ever taken. The Hubble looked at a single spot in the sky for a long time to produce this deep image, and it was able to see back in time to a point where the universe was about 1 billion years old. So between this epoch of, this is the fossil record of the universe, if you will, and between this epoch and this epoch, there's a mysterious unobserved epoch called the cosmic dark zone. And it's important because it is at this time that the first stars and galaxies formed. And the reason we've never seen it before is we've never had the right type of telescope. And that is much of what JWST was designed to do, to observe the cosmic dark zone and see the birth of the first stars and galaxies in the universe. I'm not going to show you a lot of heavy-duty science, so don't get nervous. But when we say that the JWST is going to observe the first galaxies, we don't mean that after launch you will open a copy of the New York Times and see a picture of the first galaxy. What we mean is shown on this plot, where we will look back in time with the JWST and measure the rate of star formation per unit volume in the universe as we look back in time. And at some point we will see a precipitous drop-off, and that'll tell us that we've reached the formation epoch. And as we look back in time and fill in the data here, we will be able to discriminate between different models of how the universe began and how stars and galaxies evolved. We can simulate that with giant supercomputers. And this is a supercomputer simulation of the birth of the universe. We see that the material in space is distributed in a spider web like fashion. It's called the cosmic web, and that traces the distribution of dark matter in the universe, and the matter that we can see follows that. Now, when we look at galaxies nearby today, we see their very symmetric shapes or morphologies that you see in your textbooks. Some have spiral arms, some don't, some have bulges, but they're very symmetric in regular objects. When we look at galaxies as far back as Hubble can see, they don't look like that anymore. Those beautiful shapes are replaced by sort of irregular morphologies, little blobs that look beaten up, but they don't have those regular shapes. And this is another example of that, where here in the present day, a galaxy that looks like this, as we look back in time, it kind of looks like that. One of the things that we want to study as we look back in time with the Hubble Space Telescope is what's causing this change in how galaxies appear. Nearby, we could see that a lot of these irregular morphologies result from collisions between galaxies. And we can actually simulate those collisions and produce these irregular morphologies. So we think that this phenomena is resulting from collisions of galaxies that were more common in the past. And JWST will help us understand if that's correct. Now, the light that's emitted from these very distant primeval galaxies is emitted in the ultraviolet part of the spectrum. But as it travels to us through the expanding space, the wavelength is stretched into the infrared. So to see it today, we have to build an infrared telescope. That's one of the reasons why Hubble cannot see the cosmic dark zone. It's not an infrared telescope. Now, the spaces between the stars, the so-called interstellar space, it's not an empty vacuum. It's filled with giant clouds of dusty molecular gas. This is a famous picture of one called the Eagle Nebula that the Hubble Space Telescope took. And this is dust-filled molecular gas. Now, how do stars form? The way they form is that we have these giant clouds in space, and they collapse onto themselves due to self-gravity. And as they collapse, the pressure inside the cloud increases. And so the temperature increases. It's just like if you fill your bicycle tire at the gas station, the tire feels a little bit warm after you pressurize it. Well, in the center of these clouds, the temperature can reach very high temperatures so that nuclear fusion occurs, and that's how stars are born. We know the basics of how stars are born, but we don't know the details. We know that when they are born, there are debris, disks of debris left over. There are big outflow jets that occur that we don't completely understand. And JWST will do a lot of science in this area. But the infrared capability that allows it to see those primeval galaxies is also very handy for looking into these molecular clouds, because in the infrared we can see right through the dust into the star forming action. And so that infrared capability that we put in to observe the early universe is very useful for lots of other science. Now, this is an artist's rendition of the debris disk around our own star, the Sun. This is material left over from the formation of our solar system. This is an artist's rendition, and this is an actual map of where that debris is, to the extent that we understand it. The so-called, these rocks and chunks of debris are called trans-Newtonian objects, and they're sometimes called Kuiper belt objects. And they're of great scientific interest because they are primordial pieces of material left over from the birth of our solar system, the Earth, and everything that we know. So we want to study that with JWST, and NASA wants to study it with all of its missions. Recently, we launched, long time ago, we launched a mission called New Horizons to study Pluto. And it took many, many years to get to Pluto, and it was just recently there. And after it revolutionized our understanding of Pluto. But after it finished with Pluto, we had it fly by one of these Kuiper belt objects. And this is what we saw. Two boulders sort of stuck together like that. This is of great interest because one theory of how planets form have planets formed by agglomeration of chunks of material like this. This is the most distant object that humanity has yet explored by actually going to it and looking at it. So it was a remarkable achievement that we were able to do that. And we're still figuring out what we've learned from the imagery on this. This is a computer simulation of the formation of this object, and we find that this object can result from a very low velocity collision between these two rocks in this computer simulation. These rocks collided at less than 10 meters per second, and this is of great interest to people who study the planet formation theory. Now, when I was a graduate student, there were no planets known outside of our solar system. Now there are thousands and thousands. Now we know that all stars have planets, and we've also figured out how to search for life on very distant planets. So now a whole new field of science has been born. It's called exoplanet astronomy, and much of that science has to do with the search for life. And so the search for life is not some Buck Rogers fantasy. It's very much a major focus of NASA right now. So how do we search for life on something that's very, very far away? The JWST will be able to do spectroscopy of atmospheres of other planets. Okay, so what does that mean? When we do spectroscopy, we record the light and we spread it out into its component wavelengths so we can observe it, sort of one wavelength at a time. And when we do that, we find lots of bumps and wiggles. And these bumps and wiggles are due to emission and absorption of light by individual atoms and molecules. And so by studying atoms and molecules in the laboratory, measuring how they absorb and emit light, and then comparing that to the spectra of distant objects, we can actually identify the atoms and molecules in the atmospheres of exoplanets and in all sorts of astronomical objects. So this is a spectrum of the Earth. If the Earth did not have an atmosphere, this would just be a flat line. It's not a flat line, and we can identify all these atoms and molecules that produce that. And so when we look at exoplanet atmospheres, of planets around that are orbiting stars other than our own, we'll be looking for chemistry that can only be there in the presence of life. And that's the main tool for the search for life. The JWST wasn't really designed for this because back in 1996, this was still sort of fantasy. It's not fantasy anymore. But the JWST can make enormous strides in this area. The JWST can detect liquid water on an exoplanet that is just a few times the size of the Earth. Why do we care about water when we're searching for life? It's not because alien life might get thirsty and need something to drink. Rather, it's that for the organic chemistry of life to occur on a planetary scale, one needs a solvent to be available on a planetary scale, and water is what we're most familiar with. This is a simulated spectrum of what JWST would see on a planet like the Earth with water. And so this will be a major area of science for JW. And if there are any young astronomers in the house, exoplanets is probably a good thing to go into because it's an exploding field right now. Now, when we first put pencil to paper on what kind of observatory we had to build to do that science, we realized that we had some big problems that almost stopped the project in its tracks. First, we determined that to see those faint galaxies in the cosmic dark zone, we needed 7 times the light gathering capacity of the Hubble Space Telescope. We needed Hubble's ability to see fine detail, angular resolution they call it, but in the infrared, which also necessitates a giant mirror. And then because we have to observe in the infrared to see those first galaxies, we needed an observing capability that spanned the optical all the way to the mid-infrared spectrum. This shows the size of the JWST mirror compared to the Hubble mirror and a man. Now, to meet these requirements, we had to solve these two problems. This giant mirror is bigger in diameter than the biggest rocket. So that was problem number one. And problem number two, to build an infrared telescope, the telescope has to be very, very cold, because everything above absolute zero emits light. And warmish objects, like we have in this room, emit infrared light. If we had infrared goggles on, we would see our bodies glowing, the wall and floors would be glowing. So if we didn't make the JWST cold, it would be blinded by its own infrared emission. How cold did we have to make it? Almost minus 400 Fahrenheit. Really, really cold. And it still is no mechanical refrigerator that can cool something as big as the JWST to such a low temperature. So for the project to be realized, we had to solve those problems. Let's talk about the thermal problem first. The JWST will not be in orbit around the Earth the way Hubble is. We are going to send it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. Don't worry about that. It's a point in space that's about 1 million miles in the anti-sun direction from the Earth. And there it will orbit the Sun. Now, why did we do that? In this configuration, everything that produces heat on the JWST, the Earth and the Moon and the Sun, will always be in the same direction. So we realized that if we could deploy a giant sun shield that would cause the observatory to always live in the shadow of the sun shield, then it would cool passively to the desired temperature by simply radiating to the cold darkness of space. Okay, so the JWST has to always live in the shadow of its sun shield. And in fact, once it's cold, if the sun shines on it, it will probably break. So, and now at the same time, we have to point this telescope all over the sky. So we designed this sunshade so that we could tilt the observatory 5 degrees toward the sun, and we're still in the shadow. We could point it 45 degrees away from the sun, we're still in the shadow. So now we can cover an arc on the sky 50 degrees long. And you can see that if we rotate about the Earth-Sun line, which is this line, that's not going to spoil our shadow situation at all. So now this arc turns into a big annulus that covers about 35% of the sky. So at any instant in time, the JWST can point at 35% of the sky and still be in the shadow and be fine. And now as we rotate around the sun, as we orbit around the sun, now we're rotating about this axis, this annulus will cover the whole sky every 6 months. So every 6 months, the JWST can point at any spot in the sky. Now we're not going to put the JWST exactly at the L2 point, but we're going to put it in a little orbit around the L2 point. And the reason for that is we have to stay out of the shadow of the Earth because we're generating electricity with solar arrays. So if we get into the shadow, that would be bad for business. This orbit around the L2 point is an unstable orbit. It has to be maintained with station-keeping thrusters. And the propellant for those thrusters is the expendable material that will determine the operational life of the JWST. When it runs out of propellant to maintain the orbit, then the mission will be over and the JWST will fall out of this orbit and just be left in some random orbit around the sun. We have that propellant tanked up for about 10 years of operation. So the JWST should last for about 10 years. Now, to deal with the giant mirror and fitting that into a too small rocket, we adopted a segmented mirror architecture. So instead of making one giant mirror, we made 18 hexagonal segments that could play together as if they were a single mirror. And then we designed a system that would fold up inside the rocket fairing. This is an end view. So you can see there's not much space left over in that rocket fairing after we fold the JWST up into it, but it does fit. We're flying on a French rocket called the Ariane 5, and it will be launched from French Guiana, which is on the east coast of South America. The payload is about 6.5 metric tons. It's launched warm and then will cool to minus 400 Fahrenheit after the sunshade deploys. And next I'll show you the origami of how all of this deploys in space. That origami involves 40 deployable structures and 178 release mechanisms. Every single one of them has to work. If it doesn't, the astronauts can't go to the L2 point to fix this the way they did with Hubble. So let's take a look at how that works. First, the solar arrays come out so that we can become power positive. We're operating on batteries prior to that point. And there are some trajectory correction maneuvers that have to occur to navigate ourselves out to the L2 point. A high-gain antenna deploys so that we could begin communicating with the JWST. These pallet structures that you see unfolding contain that giant tennis court-sized sun shield, which is folded up inside them. This telescoping boom provides thermal separation between what will be a very cold telescope and what must remain a warm spacecraft, which contains computers and other electronics that have to remain warm. These telescoping booms are pulling the sunshade out of the containment pallet, and then these spreader bars are separating the 5 layers of the sunshade that allow it to achieve the thermal performance. This sunshade is like a giant sail, so we have to take that solar pressure into account. This is a little trim tab that helps us balance the JWST against the pressure of the sun. Now next you'll see there's some radiators that deploy to help us cool the JWST, and this is the secondary mirror of the telescope deploying now, and the wings of the giant mirror deploy in a manner similar to a round drop leaf kitchen table. This of course is greatly sped up. This will take about a month in real time, but that's basically how it works. Now the JWST is about $8 billion to launch. It's the most expensive science project that the US government has ever done, and it's too big for any one agency to do. So the JWST is an international partnership involving the European Space Agency, who is providing the rocket and 1.5 science instruments, and the Canadian Space Agency, that is providing the fine guidance sensor that helps us point the telescope, and then NASA is doing everything else. And the observatory will be operated from the Space Telescope Science Institute in Baltimore, Maryland. All right, let's talk a little bit more about the telescope. This is an actual picture of the JWST flight telescope in a clean room at Goddard. You can see the 18 segments of the gold-coated mirror here. Now, for telescope fans, this type of telescope is called a 3-mirror anastigmat, and it works like this. Light from the distant objects comes in parallel, and it reflects from that giant mirror to that secondary mirror that you saw unfold in the video, and then it passes through a focus to a tertiary mirror that you can't see here, hence the name 3-mirror anastigmat. And in our case, we send it to a 4th mirror, which is articulated under computer control so that we can stabilize the image against vibration from machinery running in the spacecraft. And then that light goes to the science instruments. Now, the JWST mirror is not made of glass, the way the Hubble mirror is, and the way most mirrors are. It's made of beryllium. And the reason that we had to make it out of beryllium is that we're going to operate this mirror at -400 Fahrenheit. So we needed to find a material that had a low coefficient of thermal expansion at that low temperature. And beryllium has that. And so we chose beryllium for this mirror. Beryllium is toxic. It's very difficult to work with and machine. It comes in a powder form, and we compress it under tremendous heat and pressure to make a giant block of beryllium. And then we machine away almost all the beryllium that's there to create a very lightweight structure that's open like this on one side and polished on the other. Weight is a premium for anything that flies, either in space or in airplanes. So this was a major technology challenge. And the figure of merit here is called areal density, mass per unit area. And the JWST mirrors are a new state of art in terms of achieving lightweight mirrors. They're about 6 times lighter than the Hubble mirrors. Now, if you're paying attention, we said we're going to operate the telescope at -400 Fahrenheit. Now we have to polish these mirrors. How do we polish mirrors? We rub on them with gritty stuff until they get smooth and shiny enough. Well, that's a room temperature operation. So if we're going to polish the mirror at room temperature and then use it at -400 Fahrenheit, it means that we have to put the wrong shape in at room temperature so that we get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling isn't perfect. And so we've had to follow an iterative process where we polish the mirrors part way and then put them in a specially instrumented space simulation chamber at Marshall Space Flight Center that allows us to cool them down to the operating temperature, observe them with special optics test equipment to see how our polishing is tracking to our model. And we took many years to do this through many iterations to finally achieve this result, where this is the ambient shape that we polished in, and this is the desired shape at the operating temperature. And so this was a new achievement and one that we've been successful at. The structure that holds the mirrors was also a big technology challenge. If we tried to make the structure out of aluminum, the JWST would be much too heavy to launch. So we had to invent a composite material that would hold the mirrors against the loads they experience when we launch them, could undergo 300 degrees of temperature change without distorting, so that the mirrors could end up in precisely the right position. And we managed to do all that, and we were able to actually realize this structure that performs in that way. It's quite a difficult thing to build. It involves more than 3,000 parts that have to be, in effect, glued together in a very, very precise way that can withstand the rigors of launch. And all that work is behind us now. This is an example. This is a clean room video. This is a walkout deployment test of that secondary mirror deployment design. And it's just an example of some of the testing that we do to make sure that we really understand what we're building. This is a robotic pick-and-place machine that we used to attach the 18 mirror segments to the backplane structure. These are the actual flight mirrors. They're covered with black covers to keep them clean. And this robotic arm has a very high precision end effector on it that is helping the technicians get the mirrors in exactly the right place so that the observatory can work properly. You get the idea. And this is an example. This is an example of a typical craning operation in the clean room. That's the actual JWST telescope being put onto a turnover fixture so that we can do some testing with it. Let's talk about that sunshade. This is one of the riskiest parts of the whole JWST mission. Its 5-layer sunshade has an SPF of 1,000,000. So if you had this on the beach, you would be very well protected. It's literally the size of a tennis court, 73 by 40 feet. It's made of a plastic material called Kapton that's thinner than a human hair. And these sides that are shown silver are coated with vacuum deposited aluminum. The pink side is covered with silicon, and it actually looks pink in reality, and that helps that Kapton material withstand 10 years of sun exposure. The sunshade has to have a very precise shape so that stray light reflecting off it can't get into the telescope. And as those of you who sew know, to make a curved thing out of flat cloth, you need to do a quilt with lots of seams. And this sunshade is actually a quilt of more than 50 pieces with 7,000 inches of seaming. Instead of using needle and thread, we used thermal spot welds. But this was an enormous undertaking to build the sunshade, and that work is behind us now as well. This is a video of a pull-out deployment test of the sunshade. These tables are providing gravity offloading. They weren't there in space. This is the sunshade folded up in that pallet structure. And here we're learning and practicing how to fold it so that when it gets pulled out in space, there won't be any surprises. You can get a sense of scale by this person who appears in the middle here. And if you look closely, you can actually see the quilting as well. You get the idea. All right, the telescope, the function of that giant mirror in the system is to collect the light from the faint objects that we're going to be observing. And it sends that light to the science instruments, which are located on the business end of the telescope, the back of the telescope here. And those science instruments help us extract the physics information from the starlight. Everything we know about the universe around us comes to us encoded in starlight. And what modern astronomers do today is extract through various tricks and methods the information that's in that light. And so these science instruments record the light, they process it to facilitate that extraction, and then they also digitize the light so that we could send these signals to the ground via radio transmissions. This is what the science instruments look like. We have the near-infrared camera here. This is the instrument that will image those first galaxies to form in the early life of the universe. The whole instrument is made of beryllium. It's actually 2 cameras, one on each side here. It's fully redundant because we also use that camera to adjust those 18 mirror segments to get them to play together as a single mirror. This is one of the most unusual instruments on the JWST. This is the near-infrared spectrometer. This is an instrument that will measure the spectra of exoplanets, and it will also measure the spectra of galaxies and everything we look at. Now, we had a problem in trying to look and understand these primeval galaxies in that they're very, very faint. So to get a useful signal, we have to stare at them for a long, long, long time. And if we tried to observe those galaxies one at a time, we would never get a large enough sample size within the 10-year mission. So we had to design this instrument to observe 100 targets simultaneously in a single exposure. It's called multi-object spectroscopy, and this is the first multi-object spectrometer to fly in space. It's also unusual in that it's made out of an advanced ceramic material called silicon carbide. Everything here, the bench, the mirrors, everything in that instrument is made of this ceramic material. When I say ceramic, not unlike your bathroom tile. You can't drill and tap a hole in ceramic, and so most of this instrument is held together with friction. That's also a first for us. This is the mid-infrared instrument. This will give humanity its first high-definition view of the infrared universe. You know, those beautiful photos that you see from the Hubble Space Telescope, those are UV optical light. We've never seen that fine detail or angular resolution, if you will, in the infrared. This instrument will open our eyes to the infrared universe and show it to us in a way that we've never seen before. This is the Canadian's fine guidance sensor that helps us point the telescope. This can sense pointing to a millionth of a degree, or about 4 milliarc seconds. And this has some science functions in it that are geared specifically towards studying exoplanets and their spectra. This is what the instruments look like when they're assembled into the module that's attached to the back of the telescope. And this was delivered in March of 2016, and it's been working great ever since. Now, to test the instruments, we've had to use, again, a space simulation chamber. The biggest one at Goddard is 27 feet by 40 feet long. And even that giant chamber isn't big enough to hold the telescope. And so we had to test that instrument module in this arrangement here, where it looks down at a simulator of the JWST telescope. And of course, all of this had to be cooled to that minus 400 degrees Fahrenheit. So these simulation chambers have shrouds inside them that are cooled with liquid helium and liquid nitrogen to achieve that cooling. And this is an actual photo of what the lower part of this chamber looked like. And you can see that these are very complicated setups. And this is some of the most difficult cryogenic testing that NASA's ever done. We had to test that instrument module 3 times for 100 days each, with the team working 24/7 for those tests. Now, when we finished testing the instrument module and bolted it to the telescope, then we took advantage of the fact that the telescope is designed to fold up inside a rocket, so we used a special shipping container that can hold the JWST safely, provide the special environment that it needs to remain ready for flight. It's a truck-mounted container, and it fits into a C-5 jet transport. It just barely fits in, as you can tell, but it does fit in there. And we use that to fly from Andrews Air Force Base to Houston, Texas, so that we could test the JWST in the largest space simulation chamber in the world. It's called Chamber A, and it was built to test the Apollo command module. This is a picture of looking through the door of Chamber A with the Apollo inside there. And this is actually a man-rated chamber. On Apollo, the astronauts actually were in there when they simulated the space environment here. We're not using it that way, and we had to pull that chamber out of mothballs, refurbish it to test the James Webb Space Telescope. The James Webb has already rolled into that chamber on rails, and it hangs from the roof of the chamber on rods and observes special optics test equipment in the roof of the chamber, so that we could do something called an end-to-end optical test. The mental image that you have when I say that is exactly the right image. We're shining light through the telescope just the way it will occur in flight, and we're making sure that everything is working perfectly. Of course, all of this in the cold environment. That's a very difficult test to do, and it's a test that we skipped on the Hubble program, with consequences that I think most of you are aware of. Since the astronauts can't fix this thing, obviously we're not going to skip, did not skip that on the James Webb Space Telescope. And so this work is all behind us now. This testing went through a giant hurricane that flooded most of Houston that I think you remember, but it didn't interrupt our testing. Okay, once we finished that testing, we went back into the airplane and flew to Los Angeles, California, where our contractor, Northrop Grumman Aerospace Systems, is now integrating to the telescope the spacecraft and the sun shield. This is what the clean room looked like out at Northrop Grumman, a month or so ago. This image is blurry because we're not allowed to show you an in-focus image. This is the actual flight sun shield. Everything pink here is actual flight stuff folded up into its pallet. It's partially deployed. This silver spidery thing is a mass simulator that's standing in for the JWST telescope. And so in this configuration, the sun shield and the spacecraft had to be vibration tested, acoustic tested, and thermal vacuum tested. And that work is just finishing up now. When it is finished, this mass simulator will be removed. The JWST telescope will be put in its place. And this will be all folded up to produce this level of assembly, which is what we launch into space. And so we're almost done, and we're in the home stretch now. After we finish up that testing, we go back into our special shipping container, but this time we can't go on the airplane. And so we will roll this onto a roll-on, roll-off transport ship, and we'll ship out of Port of Los Angeles. We'll go through the Panama Canal over to French Guiana. It's about 6,900 miles. It'll take us about 20 days to get there, and this is the first time we've ever shipped a payload to a launch site on a ship. But it's a great ship, and it should work fine.
The efforts of thousands of people across the United States, Canada, and Europe for almost 2 decades achieved this milestone. The optical and science segment of the largest space telescope ever constructed stands complete in one of the largest clean rooms in the world, ready to endure its toughest yet battery of testing. Getting to this point wasn't easy. Never mind the logistic and construction challenges this international endeavor presents. Before astrophysicists' dreams of building Webb could be realized, 10 technologies that did not exist needed to be created and perfected. They were. To give you a sense of where we are in the mission, the Webb telescope consists of 3 main segments: the spacecraft bus, the sun shield, and the telescope, which includes Webb's instruments. This telescope segment of NASA's most ambitious space observatory stands complete and tall in the NASA Goddard Space Flight Center clean room. An international team of engineers built and tested this revolutionary telescope segment. Beyond spaceflight hardware, the Webb mission required building assembly structures, test facilities, transportation enclosures, engineering copies called pathfinders, and even a miniature test-bed telescope. Revolutionary, lightweight composite material capable of maintaining its shape to 1/10,000th of a human hair at temperatures near absolute zero forms Webb's backplane and science instrument support structures. Webb's mirror segments began as beryllium ore mined in Utah. They crisscrossed the United States to be formed, lightweighted, polished, gold-coated, and finally, perfectly placed on the backplane structure with the help of a robotic arm. 4 state-of-the-art science instruments from NASA and its international partners, the European Space Agency and Canadian Space Agency, were installed and tested, each loaded with advanced components and detectors, and capable of operating at temperatures near absolute zero. Scientists will use these instruments to tease out answers to astronomical mysteries near the edge of the visible universe, in galaxies closer to home, around planets orbiting our star, and others like it nearby. The Webb telescope segment now stands complete. After launch phase environment testing at Goddard, this segment will endure more cryogenic testing at the NASA Johnson Space Center. Later, the telescope will travel to Northrop Grumman in Los Angeles to be mated to its sun shield and spacecraft bus, thus completing the observatory's assembly. The James Webb Space Telescope, our new eye on the universe.
All right, now, young people in the house, don't be concerned that JWST is going to answer all the questions. There'll still be questions after the mission is over. You know, what happened before the Big Bang? What's at the center of a black hole? What's our cosmic destiny? The universe is expanding, the expansion is accelerating. What's our future? What are space and time, and are we alone? There'll be plenty of questions to answer after the JWST mission is over. And if you're in the audience here, you can be part of the quest for answers. The people that build missions like this come from all backgrounds, all walks of life, and you could be one of them. There's a quote here I like to read. The book of nature lies continuously open before our eyes, but it can't be understood without first learning to understand the language and characters in which it is written. It's written in mathematical languages, and its characters are geometrical figures. That's as true today as when Galileo said it 400 years ago. If this is an area that you'd like to work in, go to college, study science, engineering, and math, and you could be part of the team that answers those future questions. All right. When the JWST is launched, we will see the beginning of everything, but this is the end of this presentation. You can follow the action at NASA Web, #JWST, or by going to our website, and I will answer questions for as long as you have them. Yep.